I guess you had an easy day this morning because poor Jim is sick, but I am not yet. So we will continue. In fact, today was called something else, but it's now differences yet again, since we finally got the differences last week. So the plan for today is to go over some extensions to the basic differences framework. In particular, talk about tests of what are called pre-trends, placebo tests, triple difference, standard errors for differences. Hopefully you had a chance to read the Werner, Ash, and Polsky article, which I'd like to go through in some detail as an example, as a really good example of triple difference showing up in a clinical. They did a really nice job, but they also published it in a clinical journal. And then at the end, I'll show you some cool tricks with Stata involving margins command. Before we get into the nitty-gritty, though, what do I want to talk about? So Tuesday, public service announcement, the first data analysis thing is due, and then a week from Tuesday, the first piece of the research proposal is due. We haven't talked much about the research proposal, and so I just wanted to say a few words about it, also entertain any questions, or at least encourage you to start thinking about it. So there's a little bit of a chicken and egg problem here. I'm asking you in the research proposal to go after a causal related question. I really want, that's part of what I really want you to do, because what we're focusing on by and large up through spring break has been setting up research questions that are particularly causal in nature and trying to go after them. We haven't gone through all the material yet, so I don't expect you obviously now to know what we're going to be talking about in next week and the week after, but we'll really be getting, besides differences, which is a key technique, we'll be talking about panel data methods generally, and then also instrumental variables. Instrumental variables is another key technique, also as panel data, in trying to go after causal questions. So really what I want from you is, for the first round, is a sense of the question that you're interested in going after, and some sense of the data set that you might be using to go after it. Realize this is a research proposal, right? So it's not supposed to be, you don't have to have the data in hand. This isn't something you don't need to actually do the analysis ever. Maybe you already have a research proposal in your back pocket. If it already has a causal aspect to it, I'd say shine it up real nice and pretty, because what I want you to do is think about how you're going to go after, answer this question that hopefully you are interested in. Now, there are a few examples, like today we'll talk a lot about the techniques associated with, or the differences technique is really one of its key or typical applications is in policy evaluation. So one type of question is to simply, how does this policy affect this outcome? Pick your policy, pick your outcome, figure out the right set of data, and away you go. It's pretty straightforward once you kind of get the recipe down for doing it. You may not have any particular interest in policy evaluation. You may not have any particular interest in causal questions in general, although I would argue that you probably should have some particular interest. I mean, you can't make a career out of descriptive statistics, but it's not that, I mean, the easier it is for anyone to do, the harder it is for you to stand out for doing it. Start thinking about it, turn in something that's at least plausible a week from Tuesday. If you're not sure, come talk to me. If you're not sure even then, and you have a couple different ideas, sketch them down, we can talk more about it. Because really the way this is gearing is that I may have lulled you into a sense of complacency or just somnolescence in that blah, 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 every Tuesday and Thursday. That's going to stop. We'll have spring break. That'll be sweet. I mean, that's a quiet period where we can all go back to sleep. But then afterwards is really when you guys got to start doing some heavy lifting. We'll have a few guest lectures for a couple of weeks, and then boom, it's going to be time for you guys to do it. So I'm trying to tell you there's rough water coming, so get your canoes ready kind of thing. So hopefully I'll keep my public service announcements going, but on a daily basis, or on a class-by-class basis. All right, so any questions about the research proposal business? Everyone's got great ideas. They've already written up the proposals and know how to use them. They're already analyzing them. All right, well, yeah.
I have actually a question about the assignment for Tuesday.
Okay, that's more proximal, sure.
Do you have guidelines about how long?
You know, no. I mean, I think like as much as you need to, like this is an intermediate output. Like, I'm not saying I don't care about spelling or, you know, you should write, you know, changing, it should look nice enough, but this is as much for you as for me, kind of checkpoint. And, but, you know, it's more important that the pieces are all, you have something to say. Like, research question, I don't know. We should talk about that. All right, anything else before we? Oh, yeah.
About the regression.
Oh, from last? Yeah.
Just a question, like, are there ways to get around regression? If you're trying to study something,
We'll talk about that today in the context of different differences. It's not so. Again, the point I want to communicate about regression to the mean is it's not. It's a feature of the setup, right? So it's there. It's built into looking at, you know, kind of the setup of looking at performance from an initial measurement to a subsequent measurement. There's going to be regression to the mean. It's an empirical question as to how much. The question then is sort of how do you, so know that there might be regression to the mean, how do you account for that? And the answer really is to say like it's going to be a control group. Someone else who's also in a similar situation, but you know, didn't get whatever the intervention was, what happened to their performance at the same time? So it's, you know, regression to the mean is a feature of the data. How are we accounting for that? And being able to confidently say what we're observing is not regression to the mean, but rather after accounting for regression to the mean by virtue of a control group of some sort, we see even still there's a difference in the outcome accounting for that regression to the mean. And yeah. All right. Okay. So let's go back to differences and a few odds and ends related to that, or extensions. So I think Lisa asked last time about how much data do you need on the pre-period. Well, you didn't quite say it like that, but it's kind of like that, right? Sort of simply, how do we know? Well, I think this. How much data do we need? And I said there's no single right best answer as to how much data. There's no rules of thumb about you should have more data or less. But the point I raised then, and what I want to go back to now, is the idea that the more data you have on the pre-period, the more convincing you potentially can make your argument be. Because our identification assumption here on all this stuff is that we have a control group that accurately represents the counterfactual, that is what would have happened to the treatment group had they not gotten the treatment. And so one of the assumptions built into the difference of differences is that the pre-period trends between these two groups ought to be equal or parallel, so that when one goes up, the other goes up. Well, the more data you have in the pre-period, the more opportunity you have to demonstrate how good the treatment and the control groups are in terms of the control group is for the treatment group as representing the counterfactual in anticipation of the policy. Now, there's a natural trade-off here, though, because there are other things that are going to be affecting your outcomes. So the farther back you go, the more likely it's going to be that there are going to be other features, maybe other policies that you're not interested in, that you're not accounting for, that are going to be also operating on outcomes and may differentially impact your treatment and control group coincidentally. And so there's kind of like, there's no requirement that you have to have equal number of time periods in the pre-period than in the post-period. But I think there is a kind of a default symmetry expectation of like, if you have got 10 before, you should have 10 after. It's not, because that's not required, nothing mechanical about it. You could have 1 before and 10 after. Usually I think 3 is kind of minimum sufficient to establish, idea of a trend, but again, that's like, well, you may only have 1 pre-period, you may have 2, and the closer they are together, the better off you are. So having said that, let me show you a little bit about the mechanics of how you'd actually go about doing this parallel pre-trends assumption test. So let's suppose we have 2 time trends. T sub pre is the pre-period time trend, T sub post is the post-period time trend. And we're going to do with the restricted-unrestricted model comparison test. So we have 2 model specifications. oops, the restricted model specification, we're saying there's a common pre-trend and then a main effect for a post-trend, then we're interacting the policy intervention, D, which is the dummy variable 1 or 0, with the post-period trend. There's no interaction in the restricted model because by assumption we're saying that the two groups share that common trend. We can compare that to the unrestricted model specification where we add an interaction term for the D times T sub pre, where we're allowing the pre-period trends to deviate from each other, and then the data will tell us how closely, whether or not if this interaction term is significant, that would suggest that we have different pre-period trends. So we have a intervention, we have time on this axis, we have some outcome over here, things are proceeding along, and then boom, things are proceeding along, and then boom. We want to know whether or not these two lines are parallel to each other. In the restricted model, we're not letting them be different. We're saying that we're estimating an average, an average point in the middle of them, right there, whatever that is. By adding the interaction term, we're letting them deviate from each other. We're letting the data tell us whether or not they deviate significantly. Note carefully, I didn't say anything about how you want to specify the pre-period trend, or the post-period trend for that matter. So there are a couple of different things to think about in this dimension. This again is an art versus a science kind of decision. Do you say, let's specify the pre-period trend as a linear variable, just time? So if we're forcing a line here, which might go, because of our nonlinearity, it makes it a flat line. Do we put in a vector of indicator variables where each time unit has its own dummy variable? We could do either of those. There's no right answer to that. And the other question, another question, not the only one, but another question is also how much, you may have data that are at a very fine level. At what level up do you aggregate those data? Do you want daily, weekly, monthly, yearly? Those are, the wider the time interval, the more observations, the more data you'll have per time interval, but the more variation you'll be missing within that time. So maybe seasonality matters. Maybe it doesn't. If seasonality matters, you might want a quarter level kind of data. You might also you're going to be constrained to some extent by the kind of data that you actually have. Hospital discharge data that I use tends to only have quarter level analysis. So I could roll things up to the year, the half year, or the full year, but I can't go down to the month or the week. And so, so I'm not proposing that you go fish around and find the best, the version of the test that gives you the answer that the lines are parallel in the pre-period. But I am saying that you need to kind of maybe look at the data and have some sense of what it is you're going after, what the right level of time aggregation is, and how you might want to specify the form of the pre-period trip. David, you have a question?
When you work with hospital discharge data that is monthly, have you seen a strong seasonal trend? And then have you seen the fact that February has 28 days and the fact that other months have 31 days, that makes a significant?
Well, so the first question it's really going to depend on the question, right? So if you're talking about stuff like duty hour reform, there's a lot of within-year variation. Interns come on in July, they're killing everybody, and by June everyone's living, and then the next crew comes in, and so there is that, there may be that kind of cyclicality built in. There may be things like weather patterns and seasonal differences in the disease state that you're studying, pneumonia. But for other questions, years are fine, right? And so it's just going to be a sense of what you're doing. As far as the number of days, I think generally you're probably going to want to, if you're concerned about number of days, you probably want to turn it into whatever your outcome is, account for that. So number of events per day or something. So you're accounting for the fact that February has 28 days or 29 days and other. But on the other hand, if it really comes down to the fact that you're off by 3 days at most, that, they may have rare events, so maybe it's, I'm not saying it won't ever matter, but that doesn't seem like it'd be a first order concern from my perspective. My guess. All right. So So let me show you a quick example of this in some data code. So again, using the Florida, New York discharge data, just so some setup stuff. I'm going to create my treatment group is what state you're in, Florida or New York. So I create a dummy variable because state is what's called a, it's in character format. The contents of the state variable are letters, and letters don't go into a regression analysis. You got to turn it into numbers. So I want to turn this indicator into a dummy variable for whether or not the discharge occurred from a Florida-based hospital. So I say generate, it's a byte, and the name of the variable is FL for Florida, and it's equal to 1 if this is a logical condition within the parentheses. It's equal to 1 if the variable state equals Florida. Otherwise, it's equal to 0. I know there are only two values in my state variable, New York and Florida. So when FL equals 1 is the same thing as state equals Florida. FL equals 0 is the same thing as state equals New York. Then I want to specify linear trends. So I'm going to say, okay, let me generate this new variable T pre, that's my pre-period trend, equals year. But I want to cut it off for years after my intervention. So my intervention occurred in at the end of 2006. So if years greater than 2006, I want to make T pre equal to 0. Because I only want legitimate values for the pre-period trend, because remember from last week I had the drug-eluting stent safety warnings came out in 2006. I'm using that as my sort of policy date intervention period. So, okay, I now have a variable that equals, 2006, 7, 8, 9, 10, or sorry, 2000, 2, 3, 4, 5, 6, and then 0 for the other years. Do the same thing for T sub post, but in reverse. Now generate a new variable T post equals year, but replace it equals 0 if it occurs before 2007. Now, so now I have these two trend variables, and I'm going to run a simple regression. Regress my outcome, drug-eluting stent, on indicator variables. So I'm turning those categorical variables into a set of dummy variables on the fly. I'm saying data replace T pre, which has the values 2003, 4, 5, 6, 4 variables with 4 dummy variables, but 3 dummy variables because I'm going to hold one out. Same thing for T post. And then this is kind of hard to read, I realize, in this font. I use a better font instead. I.fl is the dummy variable for Florida, and then I.tpost pound I.fl is the interaction of the post period trend, which is a set of dummy variables, and the dummy variable for the state. Notice the single pound means just give me the interaction. The double pound means give me the main effects and the interaction. I put the main effects in myself, so I don't need the double pound here. I could have left them out, but I wanted to show you in comparison for the next one. So then this is what's called a likelihood ratio test. It's the equivalent of what I call the partial F test when we were talking about the cross model. We were doing the restricted model, and then right after it, the unrestricted model. So the way we do this in Stata is we tell Stata to store the results from this model. We're going to call it Model A. It doesn't really matter what we call it, it's just some cheap name. I don't even know what it's storing, except it's storing important information to be able to compare the two models. That's a totally non-technical explanation. But then I'm going to go say, okay, save that information. I'm going to go and run the unrestricted model. So I've got all the same variables as before. Outcome is the drug-eluting stents, pre-period trend, the post-period trend, main effect for Florida, the interaction between post and Florida, and the interaction between pre and Florida as well. So this is the extra interaction that's saying, let me test whether or not the pre-period trends are parallel to each other. If they are parallel to each other, then there shouldn't be a significant difference that varies over time. There could be a main effect, but that main effect should be common.
Can I ask you another question?
You can ask any question.
Are you writing, like the restricted estimates, you're putting that in Stata, where you're writing restricted estimates?
No, those are comments.
Okay, those are comments.
Yeah, the double slash is a comment, just to let you know what it is I'm talking about.
But the next line?
Estimate store B.
Yeah, is that actually?
That's actually Stata code.
Okay.
So A is a name, B is a name, estimate store is a command.
Gotcha.
Okay, so it's an estimate store, put it somewhere, it's called B, right, because I'm lazy. And then LR test AB says test, compare the model fit for A and B using a likelihood ratio test, which is the kind of the generic name for partial F, for whatever, any kind of maximum likelihood model, logistic regression, probit, C-log-log, GLM, anything estimated with maximum likelihood, including regress, you can use this LR test test procedure for. And what it kicks out, which I didn't show you, is it kicks out a simple p-value, and an F statistic, or depending on the model, with the relevant type of statistics, but more importantly, a p-value associated with that test, that the null hypothesis is that this extra group, this extra set of variables is not jointly significant. So a rejection of that null would mean that they are jointly significant, and we would reject the null hypothesis that the pre-period trends are in fact parallel. Let me start with you, sorry.
Okay, so if our p-value is significant, we reject it, okay, sorry.
Reject the null.
Sorry.
Right,
Yeah.
so the null, to say it again, the null is that the pre-period trends are parallel. That is, they're not significant. The difference does not vary, the difference between them does not vary over time. That's the same, those are equivalent statements. Parallel lines, no significant difference over time. Rejection of that null would mean that there is a significant difference over time. In other words, that our pre-period trends are not parallel to each other. Dave, do you have a question?
I guess I have one question on the whole Florida. That's Florida, right?
Up here?
Yeah.
Yeah.
So conceptually, are we comparing Florida to all 50 states or comparing Florida to 49 states if we do it?
Well, in this case, I've only got two states in my data set.
Oh, okay.
Florida and New York. But conceptually, we're comparing Florida to everything else in the data set.
Okay.
But it's important for you to know what that is that's in your data set. I know it's New York.
Okay. But if you had all 50 states, would it be comparing Florida to 49 states or Florida to all 50 states?
No, it's Florida to whatever. It's not Florida to everything and Florida.
Right.
It's Florida to everything but Florida.
Okay.
So think of it as a partition.
Okay.
Because Florida is one, everything else is zero. That's your control group.
Right. Okay.
I think I'm a little confused by something you said earlier, which is, so you said you're already including the main effects of like post and Florida in there, right? So
Yeah.
I don't totally understand conceptually how adding that next term really changes things, like
This term or that term?
Both.
Okay, so each of these is saying, okay, so let's take this in without any interaction, right? So let's say we just had a trend and a state. The state would say, what's the average difference between Florida and New York over all years? But what if that difference changes over time? So what if we have, let me try and do a better job with a pre-period control here. We've got two trends, two lines, we just want to compare them. Okay, so we have so if we take these two lines, right, like this is A and this is B, not related to those A and B right there, separate A and B. Two lines, we want to know the average difference between them. One's Florida, let's just call this one Florida and New York. The average difference between them will get picked up by this main effect. Without any interaction, will get picked up by this main effect. On average, Florida and New York are different by whatever the average difference is averaged over the time period. But in reality, we can see pretty clearly that they're not, that average is missing some variation. We want to know what the difference is on a year by year, for each year, how big that difference is. And that interaction will tell us for each year, because we're using categorical variables, we're turning this category into a set of dummy variables. For each year, bang, 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 you know, in 2003, it's 5 percentage points. In 2004, it's 6 percentage points, and so on. And then that's just for the post. We're going to do the same thing down here for the pre to make sure, to test our conjecture that the lines are in fact parallel. If those were our two lines, if that was our pre-period trend, we'd probably reject the null that these two lines are parallel. But maybe not. We don't know what the scale is and all that other stuff, how much data we have. That's why we have to do the test to say, okay. Again, this goes back to my point early on of be careful of the questions you ask, because you may wish you didn't know. So if we only have 2 points, pre and post, you can say, look, this one goes down there, that one goes down there, and the difference, is much bigger, right? So the difference here is large. We don't know, if we're not able to test whether or not the pre-trends are equal to each other, then we can only conjecture. It's a limitation. If we have data that shows that they go like that, though, then we know it's probably not a policy effect that we're talking about. It's some underlying latent trend from something like, oops, it turns out we're measuring the wrong policy, or not even, because these things were going for a long time. Whereas if we found, that everything was proceeding hunky-dory in parallel, and then poof, that's a good setup, right? Cruising along, lightning bolt strikes, policy intervention, and then deviation. That's a good difference in differences. Careful what you ask for in terms of pre-period trend data.
So like that's the null hypothesis.
The null hypothesis that they're parallel. They don't have to be equal, they have to be parallel.
Sure. Okay.
So can you do difference in differences if they're not parallel? Or
You can do anything you want to. I mean, you can, so you could say, what data? We never got that data. I'm just going to use the single pre-period point and the single post-period point. And maybe it's because the pre-period trends you believe, honestly to yourself, and not because the data are telling you this, but you believe that there's too much crap going on in the pre-period to be able to estimate, like there's other stuff going on, and it's sort of would be misleading to use the pre-period trends because they're not parallel, but there's also all this other crap going on that I know about because, institutional detail stuff. And so it just makes sense to do it. So, it's a judgment situation. Like I can only teach you there's the static code, it doesn't tell me whether or not it's appropriate to use. Other questions? No? Okay. So I want to, so that's pre-trend test of parallel. Let me introduce another really important concept that has value in differences, but also has value just, I think, generally in terms of empirical research. It's scary as I'm back here. Walking around. I'll stay over here myself. This idea of a placebo test. So most of the data, most of the data, of the types of analyses that we do and see in published literature and unpublished literature are of the form of, we see the policy, we see the associated impact of the policy. We therefore presume that the policy caused the impact. But there's another type of data which you can do in a lot of cases, which is really strong if it works out right for you, which is the reverse test, the placebo test. The absence of the policy should also not be associated with what we'd expect that change would be in the outcome were there a policy there. And so the idea basically here in the context of differences is to say, okay, we have a policy, a true policy, we can test whether or not there is a response, but then we can impose what's called the placebo test. We could assume that there was a policy at a time when we know there wasn't. And if we find an effect from this fake policy, this placebo policy, we're less confident now that our positive results showing an effect were genuine because we could find the same kind of effect when we know by construction the placebo couldn't have made the patient better. The placebo policy couldn't have reduced gun violence because there was no policy like that. So, that has an obvious clinical parallel to it because it's called a placebo test, but the idea of putting it into data and testing it, I think it can be really inspiring. So a couple examples from the Journal of Health Economics. One of my favorite papers of all time by a guy who's not the most friendly guy, David Dranoff at Northwestern. So there was this big argument actually it was all the way through most of the 80s. Actually got pretty ad hominem about this concept of physician-induced demand. Whether or not physicians create demand by, abusing their agency relationship with their patients and giving them treatments that they don't necessarily need, or they wouldn't have otherwise gotten if they, because there's a whole strain in economic literature about trying to test the target income hypothesis. Physicians have target incomes where when you threaten their their income in the form of reduced pay or reduced prices per procedure? Would they respond by kind of compensating and doing more of other types of procedures, or doing more of that procedure that was less expensive to try to get back to their X $100,000 a year type income? So this actually got it got pretty ugly. There's actually some published like ad hominem attacks between well, Mark Pauly was a good guy, but there was a bad guy who was accusing Mark Pauly over Wharton of doing bad things. But Mark's too cool to tell him off. He didn't have to call him names because he totally killed his argument. But anyway, this guy Ian Graham came in and said, let me take this methodology that people have used to document the supposedly document physician-induced demand. Like, you know, more hospitals leads to more hospitalizations, and more protons lead to more protons kind of thing. And let me do this in the context of obstetrics and test whether or not areas that have more OBs in turn have higher pregnancy rates or delivery rates. Birth rates, I guess they're called. And so they found, in fact, that areas that had more OBs had higher birth rates, totally undercutting the idea. Well, unless you think that these OBs are somehow fathering, say, children, you know, really stuck a nail in the heart of this methodology. Not that the issue is not still a genuine issue, but that the methodology that people have been using to demonstrate said, you know, oh, partial physician-induced demand. Look at this. Hey, look at this counterexample. Unless you think OBs are out there really inducing demand, nip and tuck style, it's probably not really, you know, it's not so this is a cute little paper. And then my other favorite paper, by me, of course. You know, we'll sign copies later. For my dissertation, I was interested in cardiac surgery report cards. Like the paper that we read today, Werner, Ash, and Polsky, Rachel and I were actually overlapping in grad school together, but I was working on a different aspect of it, and I wanted to see whether or not referral patterns changed in response to the publication of cardiac surgery report cards. So I was using Pennsylvania, which started publishing these in the early 1990s, to see whether or not patients were more likely to be treated by better rated surgeons after report cards came out versus before, right? So were these report cards adding information to the marketplace? And so to do this, I said, okay, let me take Pennsylvania where there was an intervention, then let me also take another state, and I had data on Florida. Clearly, you know, I like Florida data. And let me construct a report card and then see whether or not referral patterns responded to the publication of a report card when in fact there never was a report card. And what I found in that case in particular was that both in Pennsylvania prior to the publication of report cards and in Florida, where there were no report cards, patients were still more likely to be treated by lower mortality surgeons and less likely to be treated by higher mortality surgeons, suggesting that these report cards were not necessarily informing, with no evidence they were informing the referral patterns. Referring physicians were either able to observe somehow there was mechanisms in place. My supposition is that it was referring physicians, referring cardiologists were able to observe, at least on the margin, who the better and worse cardiac surgeons were and steer their patients accordingly. Same idea though of, you know, it's one thing to say we have, you know, here the intervention was a report card. Does it change referral patterns? Yes. But I was able to show that if this was truly having an effect, it shouldn't have changed referral patterns in an instance where there were no report cards, the placebo test.
Wait, so what were they responding to?
I
How
don't-
did they,
What?
in Florida,
What do you mean?
in the absence of a report card?
So the absent report card, patients were already more likely to be treated by lower mortality surgeons and less likely to be treated by higher mortality surgeons.
And you think that was just sort of kind of word of mouth? Who knows?
You tell me, right? That's my.
You would contend that
The
lower
cardiologist
mortality
doesn't get
surgeons
comments.
have better word of mouth.
Right.
Right, their
There's a
patients
lot
are
of
alive
data
to tell.
For things like that.
The
People
point
rely
being
on
it's not
family
the report
friends
card.
way more than they do.
Yeah, you're not gonna be like, oh, my grandpa died after this surgeon operated on him, versus like the guy who's like jogging around, this surgeon operated on me.
So this is also a good example of
Anyway,
things.
okay, I get it.
Well, you can call bullshit. I mean, that's fine.
I'm not calling bullshit, I think it's fascinating.
Sure you are. I'm judging. You want to read it?
And you just got one.
Yeah. But it also may be, so here's another, like, sort of, let me make a meta comment here. Here's an example of, in this case, I publish this in the health economics literature. Things that you, as clinicians, may observe and say, of course this is true, and to try to publish this in a clinical journal, well, the methods were a little bit complicated, and so they would have never gone for it. But, you know, sort of like one man's trash is another man's treasure, things that may have been perceived as too obvious to make it into a medical journal got into a pretty good health economics journal because, you know, I framed it in the right way and did a lot of work and blah, blah, blah. So I guess it just goes back, I just want to underscore my periodically repeated comments about know who your audience is and who you're trying to show it for. But a research question, and think about where you're trying to place your research question. So this is of particular interest to health economists because we're interested in matching and efficiency. Report cards may also be interesting to clinical audiences as well, but you know, different aspects may be more interesting to different audiences. So let me walk through this idea with I'm calling here a Granger-style placebo test, but that's really just more words. Granger causality is just this concept in econometrics about future events future policies shouldn't be able to influence current outcomes. So, you know, the placebo test here is used a different approach to test whether a future policy could affect current outcomes. For example, whether a 2006 policy had impact on a 2004 outcomes. However, you need to take into account that, in particular, you don't want to do this placebo test and then find that there's an effect. If there is an effect, you better know why. And one thing to be careful of with any kind of difference in difference or any kind of policy evaluation really is that you know the institutional details. So you can, when you say, oh, there's nothing worse than saying there was no policy in 2004 and then having a reviewer or worse, a reader after it was published come along and say, dumbass, what about X, Y, Z? You're like, I didn't know about that. Well, you know, oopsie poopsie. Everything, you know, all my assumptions are totally wrong. A more insidious version of that is, okay, the policy got implemented in 2006, but in fact it was promulgated or you know, the legislature passed it in 2004, and there was anticipatory behavior by these, whatever the actors are. And so this is just reaffirmation of this idea that you better know what the institutions are that you're studying, especially when it gets to policy crap, because it hinges on your making some assumptions about there was no impact, there was no possible impact at this point, there was some possible impact at that point, whatever. When you get these situations, one thing to do is to say, okay, so another legislature passed in 2004, didn't get implemented in 2006. What you can do is you can do kind of a multi-stage difference in difference. You have a pre-period that's a true clean pre-period. Say, you know, no one was even thinking about this in 2003, so we'll look at 2003 to 2000 as our first pre-period. Then the period between 2004 and 2006 is this empirically determined, you know, it was being talked about, but we're not sure what happened. Maybe it had an effect, let me test. And then 2006, the policy came online, it was implemented, bang, bang. So 2006, 2008, I will then actually look at my second post period, or the late period, post-policy implementation, and see whether or not there's an example here. So there may not be a difference between the 2006 plus period to the 2004 to 2006 period because of anticipation, but by having that early clean pre-period, you have some opportunity to look at, well, there was no nice parallel lines, some sign of deviation, and then policy took effect. We don't have to know necessarily when those effects occur, because the data, that's our job as analysts, to have the data tell us what the impacts of these policies are. We need to know the timing of all these various policies or potential implications, or potential institutional details, so that we keep track of them in our analysis.
Is this like doing splines, or?
Well, you can get fancy with splines and stuff, but it's really like, all I'm talking about is just something less, less sophisticated than a spline. It's just saying.
What's a spline?
Well, it's a technique. Thanks, David.
Sorry.
So I'll get to a spline in a second, but let me go back to what I want to talk about, which is 2004, 2006, right? So these are the two extensible, legislature passed it, policy got implemented. So we've got treatment and control, everything's hunky-dory, treatment and control, you know, and then boom, and then and boom, all right? So in a difference, we're generally not testing, we could test the slope of the line, we could also just test sort of the level of the line, depending on how many data points we have here. And so, you know, levels is sufficient if there are not too many data points. It goes up like that. Like this is only a year, say, or something like, maybe these are only just like a single point, right? Or 2 points. 1 point there and 1 point here. This might tell us something about the difference in the levels, right? A spline would be saying, okay, so you can, let me start fitting lines to these points. If I have enough of these lines, instead of using levels, I can go, you know, put a line there, put a line there. That's a linear spline. A spline is also a technique to say, I'm trying to, okay, but before I start talking about spline, is everyone comfortable with that idea of just simply, we have a clean period, an intermediate period, and a post period. We're doing differences, but we have 2 different periods we can compare across middle to early, late to early, late to middle. Cool. Okay. Quick deviation to what a spline is. Suppose we had a line, we had a collection of dots, and we were trying to fit a best line to it. Like, oh shit, how do I fit a line to that, right? Maybe it's a quadratic, but I'm not entirely sure. I can fit a quadratic on that, or I can fit a straight line through it, but a straight line would look like that. But I want to respect the data, what the data are telling me. So I'm going to say, let me create some dots. Let me create some breakpoints. I'm going to put a breakpoint here, and a breakpoint here, and a breakpoint here. And that'll say, okay, let me fit a line through there, fit a line through there, fit a line through there, fit a line through there. I told the program I want knots here, here, and here, and it fits the best lines. It tells me what the slopes are of those lines in each segment of the data. To try and capture you can do it with more, you don't have to use lines, you can use quadratics within each segment. There's some issues about making sure that your little splines line up at the knot points, but it's generally a technique to try to do line fitting in an empirical way. And then the last thing I'll say about this, unless people have more questions, is that if you're really, so if you want to be really non-parametric about it, so I just showed you an example where I told the program where to put the knots, and then the slopes came out right out of the data, right? If you want to be really non-parametric about it and let the computer tell you, like, there's this cool program from the NCI, actually, from some biostatisticians at the NCI. The name of the program I'm blanking on right now. But what it'll do is it'll go through and test all, like, reasonable set of possible lines, set of possible segments to fit this, and say, this is the best fitting one with the minimum number of knots, without you having to say, there's a knot here or there's a knot there. Basically, the idea is to test whether or not there's a breakpoint in the data. You could, as an analyst, you could look at the data and say, well, I think there's a breakpoint here, here, and here, but you've told the computer where the breakpoint is. Instead, you could say, okay, I want the algorithm to tell me where the best fitting lines are, given the amount of data that I have, where the breakpoints are, where the discontinuities are, because you know, I don't want to impose my prior knowledge or my beliefs onto the data. It'll come through and say, okay, you've got a breakpoint here and here, and that's another way to test policy effects. It could be, you know, typically in a kind of a single series kind of analysis. And if people wish that I could find a paper on this, but I'm thinking of something about, like, you've got a policy that affects everybody. So you don't have a control group necessarily, right? Federal policy comes through, bang, and then you want to see, like, okay, here's the outcome, here's the outcome, here's the outcome. I want to see something there. I can test that, or I can say, like, Well, I'm not sure exactly where the damn policy occurred, right? Because it got announced there, but it didn't get implemented until later on. Let me see, well, let me run my data through the program, and it'll tell me if my data are like that, or if there's some kind of breakpoint somewhere after the policy that makes sense.
Is that join point?
Join point, yeah, exactly.
Oh yeah.
2 points for you this year. You use it?
Yeah.
It's pretty cool.
Wait, that's the
It's
NCI
a little mysterious.
program?
But
It's
it's,
from NCI.
it's,
I didn't know it was a program, but it's like it's a technique for looking at.
yeah, so you load it up and you can download it off the internet, and you got it doesn't work, of course it's not built in the state, that would be too easy. But it does just that. Okay, so now I told you what splines were. Any questions about splines before we go back to the regularly scheduled program? All right, so if you like splines, you'll love diff and diff and diff. So diff and diff and diff is exactly what it sounds like. It's a difference in two difference in differences. You understand that? You can stop paying attention. The identifying assumptions underlying our difference in differences, again, are that the control group, the experience of the control group accurately represents the counterfactual of our treatment group, right? So we're assuming away any omitted variables bias, any contamination. We can control for things to try and address omitted variables bias. We can't ever prove that it goes away. One wrinkle to doing this one wrinkle to strengthening difference in differences is to add another layer of control, a separate difference in differences. I'll show you some examples, but I'll tell you, usually it's the case where we try to do this in the context of policy evaluation when we think we can identify within each group, so like state level policy, the typical example, many of which I'll show you are, state level policies affect some specific subgroup. We can then compare within states, so we have a state policy versus a control state, pre-policy adoption versus post-policy adoption, and then within state, we can then look at the subgroup that was affected versus the subgroup that wasn't affected. So I'm working on some stuff right now involving insurance policies. Insurance policies. So this is a common one. The insurance policies and mandates are where most of the diff and diff stuff shows up. We have a situation where we're looking at state level policies on employer-based health insurance. These policies that are adopted by states by law cannot affect self-insured employers because of ERISA. And so these self-insured employers who are individuals who have insurance through self-insured employers live in the same state, are arguably otherwise identical, except that they have insurance through a firm that's not affected by the state mandate. So then we can test the effect of the state mandate on, this is mental health service use and stuff, parity stuff, by comparing pre-post policy adoption versus treatment and control state versus the employees of fully insured versus the employees of self-insured firms, if we can get these data, which in this case we can. So it does require that you have the ability to go to break apart within your treatment and control states or units some subsamples of populations. The prototypical paper was by John Gruber, who's a well-known by economist standards anyway, economist at MIT. This was in the AER, which is one of the top 5 journals in economics from a while back. It's almost 20 years. And he was looking at state-mandated maternity benefit laws on labor market outcomes. And so, again, he had experimental control states before and after the policy adoption. And he had 2 levels of comparison. So there was a period of time at which avant-garde states adopted these policies, and then later on the federal government came along and made this a federal mandate. So you got this nice staggered rollout of policies. So his first comparison was the avant-garde, first adopters versus those states that hadn't adopted. So that was his treatment, and his control was non-adoptees. But then later on, when the federal mandates came on, same paper but different time period, he then was able to compare the laggard states that were forced to comply with the federal mandate against those states that had already adopted. So he in fact had 2 control groups that were separate analyses. He could have, in theory, he could have done it in a single model, I think it would have been pretty ugly, but he had so in the beginning, no states have it, then there's a period of time where some states have it, then there's a period of time where all states have it. And then you can compare pre to middle and post to middle and get these two different sources of identification. And by able to say, like, I showed it in two different contexts, more confident that the policies are actually having an effect. And then the third difference was then looking at groups that should be affected by the policy, that were at risk to be affected by the policy, which he called married women ages 20 to 40. And then the control group was everyone over age 40 and single males between the ages of 20 and 40, because these people were ostensibly out, well, at that point anyway, were outside likely childbearing age, and these individuals were less likely to have children on their own. So, you know, so that's the third difference in this policy analysis. So then let me lay out a kind of a summary sheet for you. We started with cross-sectional, worked our way through differences, and got up to triple difference. The questions are changing as we go, and they're getting more complicated, but also tighter, in the sense of identification tighter. So in the beginning, the cross-sectional was saying, are the outcomes different in states with the policy than in states without the policy? You have it, you don't. Are the outcomes different? Problem there could be underlying differences in the population, right? So there's lots of things that we're not controlling for in that situation. We move one step up on the tree, or down in this case, to differences. Do outcomes change differentially from pre to post in states with the policy and states that don't? So now we're using the state as its own control. If things in the state are stable except for the policy change, and things in the control state are stable except for nothing because they didn't get the policy change, then that control state represents the counterfactual, and our treatment state, you know, comparing our treatment state, the change from pre to post, to our control state from pre to post, gets us around time invariant things that could not have changed in our analysis. But there could have been time varying things, right? Like other potential policies that came in at the same time the intervention came in the treatment state. So we move down one level more and add a third difference. And you can, I've never seen 4 differences, so maybe it's like those razors that go up to 7 blades or something. I think there definitely is diminishing marginal returns. And so it's not that I wouldn't ever say don't do it, but you might get more traction, unlike in poker, where like 4 of a kind beats 3 of a kind. 2 triples may actually beat a quadruple, because I think at some point it just becomes impossible to understand what the hell you're talking about with 4 different differences. Even with 3, you may be saying that's a lot of differences, and I'm having a hard time understanding. But let's see if we can try and do it, and then we'll go see what Rachel Warner and company did in their paper. The general question is, so first we have levels of outcomes in state A versus state B. Maybe I should try and go back to the board. That's working so well. So we have treatment and control. We just have we have outcome, and we have change in outcome. So we're comparing. I don't know why I did it like that, but whatever. That's a cross-sectional. That's a difference in differences. So let's just call it single diff. It's cross-sectional. And the triple diff is now going to be, is the change in outcome itself changing? All I'm doing is saying change instead of difference. So maybe that doesn't add a whole lot to your understanding, but that's what we're doing now. Is the differences in outcomes change differently from pre to post? Are women versus men differences in a state changing from in the same state from pre to post compared to our comparable changes going on in our control state from pre to post? Let me see if I can try and make that more concrete as we go through with Rachel. Yeah.
I guess as you talk it through, what's hard for me to understand is, it seems like by default, if there was a difference in difference that was just a d squared, you know, that
not squared, just multiplied, right?
So
yeah.
that if there were a difference in so let's say the non-intervention group has just no change, and then the policy group has a change, right? So that makes sense, just difference in difference. But if one is changing more rapidly than the other, is that by definition, then you're comparing the rate of change, right?
No, I'm not talking about speed of change. I'm talking about,
Well, I said the word rapid, that's.
that was.
Okay, so I don't mean that, I just mean that if your control is changing in any way, but your intervention is changing differently, then is that by definition a triple D?
You said it again.
No.
Okay,
I think
so.
what you're asking is if the slopes are slightly different, but there still has some slope.
Yeah, then is
So
that,
that can still be different.
it's still a D, a 2 to the D. I wanted to
Yeah.
square back.
That's fine, that's good. D squared.
Sounds cool.
Double D.
Double D squared.
Double
So,
D squared,
I
that's
guess I
4
don't-
Ds, that's 2 and Ds.
Right, because what you're describing was the first picture, where the lines were like this, and then the lines kind of went like
Yeah,
this.
that's the, so what I was wondering is if, so go ahead and just explain and perhaps I'll understand.
Well, let me come back to it. There's one thing
Okay.
to talk about, and now that you're getting intrigued, I want to change the topic entirely to
It's okay.
standard errors. But so let's see if we can.
I guess, is there a picture that relates to the triple D?
There will be.
Yeah, because I guess I just simply then don't understand the triple D.
You simply don't understand. Is that what you said?
Mm-hmm.
I think there's a third group.
Right. I mean,
Oh,
so
it's just that, maybe that's.
you know what? Hold on.
One more layer.
Hold it, and let me come back to it, because I have some pretty pictures
Okay.
in the discussion of the Warner paper. Let's see if we can't put it
Okay.
down. And
Okay.
then at the end of class, you still haven't gotten it, or if I,
I'll come talk to you, but I do.
or no, or we'll keep going on, because of, I suspect like this is, so, my parenthetical remark here is, I think there's still a fair amount of opportunity. Diff and diff, and even triple diff has saturated into the health service, into the economics literature pretty heavily, into health services research pretty heavily. The epidemiologists call it something different, so it's not that it doesn't exist in the clinical literature, but I still think this opportunity for differences and triple diff there's a legitimate opportunity to publish in pretty good journals in medicine using these techniques. Like there was like Gruber's first triple diff paper in '94. There's been a number of offshoots on triple diff, but it's a good thing if you have the right setup for it, and it can be quite compelling. But if you don't understand it, then what the hell, right? All right, so let's put a hold on diff and diff just for a second. I want to talk about some less important issues, which are standard errors. So when you talk about very often when I talk about standard errors, it's kind of it's an important part of the story. Standard errors don't affect whether or not the coefficient is estimated accurately, that is whether or not the coefficient is biased, but they do affect inference, right? Because beta divided by the standard error gives us our t statistic, tells us whether or not our coefficient is significantly different from 0 or significantly different from some other coefficient. Whether the estimate of our impact of whatever policy or intervention is that we're studying, whether that's significantly different from 0. So one issue we've talked about a little bit in the context of linear probability models, but shows up now and again, is homoscedasticity versus heteroscedasticity. Whether or not the variance is constant across observations. We've already talked about this, I think, a little bit, just to make sure though, in review. In cases, especially in linear regression, it's typical to use robust standard errors. That is, you just ask data for the robust standard errors, it applies the correction for you and gives them to you. That's great. One thing I want to point out from the Angress-Sapitsky book, which I think is good advice, but is not, it's kind of conservative, and it's not well followed, I think, in the general literature, is that you might want to think about using the maximum of the robust and the conventional standard errors. Because the robust standard error correction can be wrong. And so the idea basically is if it gives you smaller standard errors, that is, it gives you tighter estimates when it's supposed to be controlling for heteroscedasticity, than what you would get by not controlling for heteroscedasticity, it's probably screwing up somehow. And so the right thing to do would be to use the larger of these two things. All right, that was my public service announcement on that. There's another issue, which we'll get into more next week, but I want to draw your attention to, which is the issue of clustering, or multiple observations per per unit. We have this uncorrelated disturbances assumption, which is that the observations are truly independent, but not related to each other. Their error terms are not related to each other. Think about the simple example of patients at hospitals. So we've got 1,000 hospitals, and each hospital has 100 patients. We might likely expect that patients are more similar to other patients at the same hospital than they are to patients at different hospitals. That would violate this uncorrelated disturbances assumption. What are we going to do about it? So it depends. Well, I have a question here. There is an important question that you need to think about when you're analyzing your data, which is what is the right level of unit of analysis? So you've got 1 million patients and they come from 1,000 hospitals, so I've just increased the number of patients per hospital to 1,000. How many independent observations do you have? Depends on a couple of things. One thing it depends on is how similar patients at the same hospital are to each other, or more similar they are to each other than they are to patients at other hospitals. That's something called the intra-class coefficient. We can actually measure that, and we can account for it. So we're really interested in the patient level stuff, but this hospital level stuff is acting on the patient level stuff. We might want to just cluster the standard errors. I'll show you how to do that in a second. But we might also need to think about what the unit of analysis is that we care about. Is it hospital level interventions affecting hospital level outcomes, or hospital level interventions affecting patient level outcomes, or patient level factors affecting patient level outcomes? We may not care that these 1,000 or 1 million patients came from 1,000 different hospitals, because hospitals aren't even part of the story. These 1,000 hospitals are also scattered across 20 states. Do we also care about what state they were in? Do we care about what marketplace they were in? You can see where this could get obnoxiously difficult to comprehend. So it's not the case that every time you think of, oh, there's another layer of clustering, another layer of hierarchy, that there's nesting that goes on here, we need to do something about it. You need to, just like you need to do with your conceptual framework, think about what the minimum, sort of the simplest story is that you can tell. What are the essential aspects of that simple story, of your conceptual framework? Is it a story about hospitals? Is it a story about patients? Is it, what are the things that you care about? That's going to influence what layers of clustering you care about. Is it patients in the state because of the state level policies and not hospital level policies? And that's going to, okay. So that's going to affect what you actually want to do about clustering. What you can do about clustering, there are a couple different options. There are a variety of options, actually. This is something that we could, or you could spend a lot of time on, learning more about. There's more than I could possibly fit into this class, even this semester. And again, to reinforce this idea, whether or not this is a problem really depends on what it is you're trying to study. So you need to appreciate the layer of the kind of what clustering means in the context of your research question and the story that, the actors and institutions that are going on underlying your research question. So what can you do about it? One thing to do is to aggregate the sample to the level, to the relevant unit of analysis. So if you're talking about hospital level policies affecting hospital level outcomes, you probably want to do a hospital level analysis. There may be good reasons to do a patient level analysis if you're worried about patient level stuff. Then it's probably going to involve some more sophisticated techniques. And you may not need that level of sophistication. That's option one. Option two, you get data to adjust the standard errors for you. So you've got, all you care about is this mathematical similarity thing. Patients at hospitals are more similar to their fellow patients at the same hospital than they are to other patients at other hospitals. So we can say, dear Stata, give me the cluster. Cluster standard error. So regress y on x1 and x2, comma, cluster HOSP. That says, account for the fact that all these patients, this is ostensibly a patient level regression, all these patients are coming from different hospitals. We want to make sure that the patients from hospital A are accounted for as being more similar than, it's a simple sort of, not that simple, but a mathematical, it's simple to ask for, Stata does it for you. But there's a cost here. Or there's an assumption that needs to be in place. For the clustering, the clustering fix to work, you need to have enough different clusters. If you've got a treatment state and a control state, and those are the clusters you care about, you've got 2 clusters. 2 is not enough. How many are enough or is enough? Literature's not entirely sure. 50 seems to be a reasonable number. That's nice because there are 50 states. Depends if you want to come to DC, then you're good to go. Maybe Puerto Rico, if you have data on them, you're fine. Even 10 may be okay, but be wary of this issue because this is the kind of thing where a reviewer could say, hey, you don't have clusters. Then you gotta get into this stupid argument with the reviewer about whether or not you have enough clusters to apply the cluster standard error, blah, blah, blah. You know, so again, hopefully this correction doesn't affect anything, and you can say, all right, I did the cluster standard errors, I did the regular standard errors. It's the same damn answer, it doesn't matter, thank you very much. But this is easy, this is what people frequently do. Just make sure you have enough clusters or you have to do something else.
What is it actually doing when you say?
So I'll show you some examples of what, but basically all it's doing is changing the standard errors. It's saying, okay, the standard errors, when we assume independence, the standard errors are this. When we account for the clustering, they change by this. Generally, we're going to make the clusters larger because we have fewer degrees of freedom than we think we do. We don't have 1 million unique patients. We have 1,000 unique hospitals. So our true degrees of freedom is somewhere between 1 million and 1,000.
And it's not affecting the coefficient.
Doesn't affect the coefficient at all.
Yeah.
So then there's a whole boatload of other fancier options, which is why you might want to get somebody like a statistician or a econometrician involved, because you want to bring up the big guns. And this is where, again, this is sort of like clinical journals will vary in the extent to which they want or expect you to go out and show off. Okay, I did this, I did that. And so a lot of it depends on who the editor is and who the reviewers are that you get. Some journals have specific statistical review where they say like, well, why are you doing that? You should be doing GEE, otherwise known as generalized estimating equation, or hierarchical regression models, or more common in the econometric literature, the block bootstrap, or manually correct the standard errors using some other techniques. Like, those are all things you can do. I'm not telling you how to do them. I'll show you, or I might show you a little bit how to do GEE. But there's a whole, for each one of these, there's a whole boatload of statistical theory underlying what it is, like what the theory is and then what it is that it's doing. And so I'm not recommending that you go out and do these things without getting further guidance or something, but at least know that there was like, what the hell is GE? It's a way to account for this clustering stuff. What the hell is hierarchical regression models? A little different way to account for this fundamental issue of nesting of observations within higher levels of hospitals or states or whatever. What's a block bootstrap? Different thing, same underlying issue. Serial correlations, a similar but slightly different issue, has more relevance for difference in difference type setup, or we're looking at a longitudinal time series type piece of data. But the idea basically is if we have a unit, a state, we're following that state over time from pre to post, how many independent observations do we have? Well, I told you before that's good to have pre-data to be able to tell how much, whether the lines or the pre-period slopes, trends are parallel to each other, right? But the longer you go, the more likely you have this problem of serial correlation, which is the intertemporal, you're measuring data on the same unit multiple times, there's going to be a natural correlation in those observations because they are from the same unit. Slightly different from clustering, and yet, because clustering could be patients, right? Patients within hospitals, they don't have any natural temporal ordering to them, they're just patients. But we have more, and the fundamental issue is just how many degrees of freedom do we have? If we're following the same state over 100 years, do we have 100 observations? Are those independent observations? No, they're not independent, probably because it's the same state we're following over time. So what can we do about serial correlation? In the context of different diffs, some actually recommend aggregating up to a single pre and a single post period. So this kind of goes backwards away from this idea of let's look at the pre-trends and see if they're parallel, which still may be important. But now we're dealing with a different issue, serial correlation. What can we do about it? We can just simply aggregate up to a single pre, a single post, and then we only have 2 observations. The issues of repetition of measurement for the same units kind of disappear. We can also, this is far more common, I think this is like the natural choice, is cluster at a higher level. So if we've got 10 units of, our unit of analysis is hospitals, or let's go back to states, right? So we have states with and without the policy, when we have data on 10 years for each state, rather than treating these observations from each state as independent, we'll let them be correlated across the years within a given state. So all the Florida observations will be clustered, the 10 Florida observations will account for clustering by clustering at the state level. Same thing if we have multiple years of data on hospitals, or whatever the unit is, where we are clustering at a higher level. And then of course there are other fancier approaches, like modeling the autocorrelation or the serial correlation explicitly using time series type methods, but those I definitely won't even talk about. So let me just show you an example of how you would implement this and what happened. So I want to look at the association between whether or not you got a drug-eluting stent and your length of stay in the hospital for that index admission. If I treat the observations independently, I just say regress LOS on DES. I don't even show you what the coefficient is. It doesn't change across any of these. But over here on the right is the T statistic, the measure of significance. All these are highly significant because the T statistic is over 1.96 or 2.0, whatever the cutoff is. But I go through a series of making them harder, kind of less and less, more and more conservative, I guess. So first I just want to deal with heteroscedasticity, comma, robust. T statistics drops from 91 down to 75. Still significant, but not, still very significant, but not, not as significant. And now I'm going to ask for clustering at the hospital level. Clustering includes the robust correction as well, and it drops substantially down. The T statistic is now down to 19.9. Remember that I have like over 700,000 observations on these drug-eluting stents, and I'm using all of them here. So I'm getting a lot of this muscle. I'm getting a really big-ass data set. But I don't have as many observations as I think I do. With hospitals, I have, I think in New York, there, across the two states, there are maybe a couple hundred. Less than 400, I think, across the two states. Maybe a little bit, maybe 500, I don't know. But not 700,000. And then finally, if I cluster at the state level, which I told you was generally not a good idea because the clustering might not be accurate, the T statistic drops down to 8.7%. 8.7, which is still highly significant, but a lot closer to being insignificant than it was when I just naively ran the naive regression. How about one more class of diff and diff next week? We'll get to Werner Asher Pulse. We'll spend some time on it. But in case you care, I'm just going to show you the money shot right now. That's the diff and diff, right? So we've got two difference and differences. We compare them, and that's the diff and diff. I'll still go over this because I think it's a great paper. But basically, look, we've got this is the control states, this is the intervention state. We got pre-post, but instead of comparing levels within, so this to this, pre-post would be a diff and diff. We've now broken out within each state a black-white difference.